Hi there. This video is going to walk through thinking through some entropies of vaporization and how they relate to Trouton's rule. Okay, so first off, Trouton's rule states that the entropy of vaporization is about 88 joules per mole Kelvin for a lot of substances. Okay, so again, just a very ballpark number, but Trouton found that this was a pretty standard ballpark of entropies of vaporization for a lot of substances. Okay, and then we also have a similar situation for the normal melting point of substances. Again, we're not going to talk about this in this video, but Richard's rule similarly says that the entropies of fusion tend to be around 9 joules per mole Kelvin for most metals. All right, so what we're going to focus on in this video is looking at the entropies of vaporization for a few different substances and seeing if we can explain why some of these values are similar to or differ from Trouton's prediction of 88 joules per mole Kelvin. Okay, so here we have a lovely table with a variety of substances, their boiling points, and their standard entropies of vaporization. Okay, so a few of these are highlighted for you. So we have one highlighted here in red. So here's acetone. And acetone we see matches up pretty well with Trouton's prediction of about 88 joules per mole Kelvin for the entropy of vaporization. And we see, let's look here, let's compare with methane. So if you look at the yellow highlight, it looks a little bit low, okay, in comparison to our 88 joules per mole Kelvin from Trouton. And then this blue, we see highlighted water and methanol. Those both have standard entropies of vaporization that are a bit higher than what would be predicted by Trouton. Okay, so our goal with this exercise is going to be to try to explain those different behaviors. So we've got methane, acetone, and methanol in water. Okay, so we've got one below, one at about Trouton's value, and a couple that are higher. So first thing that we want to do is to see if we can think about what might be different between these different types of substances. Okay, so take a minute, pause the video, take a minute and see if you can think through how does acetone differ from methane, differ from methanol in water. Okay, so think about some characteristics of these substances and we'll meet back here in a minute. Okay, now hopefully you've given some thought to how these different substances are maybe a little bit different from one another, and hopefully you've zeroed in on the fact that these substances are all going to have very different interactions in their liquid forms. Okay, so when we talk about intermolecular forces that are present in these different substances, they're going to be quite different from methane versus acetone versus methanol in water. Okay, so just to illustrate that, let's maybe draw out our molecules so we can see what kind of intermolecular forces we're going to be experiencing here. Okay, so here are our lovely basic structures of these different molecules. Okay, so we see acetone here, methane here, and our methanol and our water. Okay, so if you remember back to predicting your intermolecular forces, we want to know something about the polarity of these molecules. So remember methane, CH4 is nonpolar. Okay, it's a nonpolar tetrahedral molecule. So this is going to have very weak intermolecular forces, okay, that hold it together in liquid form. Okay, so we're talking mostly dispersion forces occurring there. Okay, we're going to have probably very little ordering of those molecules. Okay, they're not going to interact very strongly with one another. If we look at our acetone, okay, this is now a polar molecule. Okay, we'll start to see a bit more orientation of these molecules in the liquid form. They'll be able to interact more strongly with their dipole-dipole interactions. Okay, and then finally looking at our methanol and water, hopefully you can recognize, looking at these, that we have some hydrogen bonding possible with methanol and water. So remember, hydrogen bonding is a very strong form of dipole-dipole interaction. Okay, so this is going to be our strongest interaction with these two. They're going to form much more ordered networks in their liquid phase. They're going to be oriented much more strongly in comparison to the acetone and the methane. Okay, so how does that translate into entropy and entropy changes when we vaporize these substances? All right, well, let's see if we can kind of picture what that delta S is going to look like for these different substances. So let's say we have our entropy of our gas. Okay, we'll just kind of put that on normalize that to one baseline value for everything. Okay, and then we'll take a look at the relative entropies of these liquid substances for each molecule. Okay, so remember, the more ordered your substance, the more oriented the molecules in your substance, the lower the entropy value is going to be, the smaller the entropy value is going to be. Okay, so our most ordered is going to be our water and our methanol. Okay, so we could say that those are going to have a very relatively low entropy. So let's say that's our water and methanol. Okay, so very ordered liquid phase. Okay, good. All right, and then if we kind of similarly think about what comes next in terms of order, that would be our acetone, right? So we've got our polar dipole-dipole interaction, so still ordered, but probably less so than with our very strong hydrogen bonding networks that we can have there. Okay, so the entropy of our acetone molecules is going to be a little bit higher. We'll have a little bit more disorder, a little bit more randomness in our acetone. Okay, so we'll increase our entropy of acetone. Okay, so that's going to be our liquid acetone. Okay, if I can spell acetone. All right, and then finally, looking at our methane, right? Very weak intermolecular forces, very weak orientation of those molecules in the liquid phase. Okay, the entropy there is going to be a bit higher. Okay, and so there's our methane, liquid methane. Okay, so as we get more ordered, that entropy of the liquid phase should decrease relatively. Okay, and then when we consider the delta S for vaporization, the change in entropy as we go from liquid to vapor, okay, that means that our water and our methanol are going to be larger than for our other substances. Okay, so this delta S of vaporization, okay, is going to be, what is that, about 100, greater than 100, okay, joules per mole Kelvin. Okay, and then here we get, is our acetone about 88, so there's our trouton ballpark, okay, and then for methane we had about 70, 73. Okay, so again, we can rationalize these values right? These relative values for nonpolar, weakly oriented liquid versus a very ordered hydrogen bonded system, okay? Thinking about the orientation of these molecules helps us to rationalize the values of delta S that we're observing. Okay, and if we were talking about something that completely did not interact, so like an ideal gas case where your molecules don't interact at all, you would get your basic kind of entropy of vaporization of about 57 or so joules per mole Kelvin. Okay, and that's strictly from just changing the volume of your system. So going from liquid to gas. Okay, so this would correspond to your volume of your gas is about, I think in our example in our worksheet we said about 1,000 times the volume of your liquid. Okay, so if you calculate the entropy change for your system, your gas going into a box about 1,000 times that size, you get an entropy change of about 57 joules per mole Kelvin. Okay, so hopefully that helped you to reason through why we observe the values for entropy of vaporization that we do. Okay, again, Trouton's rule and Richard's rule, just ballparks, right? Average kind of values for something middle of the road, okay? Like your acetone molecule that has a moderate kind of orientation of its molecules. Okay, so that would cover probably a majority of substances that you're interested in. Okay, again, depending on the orientation or lack of orientation of your substances, molecules in your substance, you'll have a correspondingly higher delta S of vaporization or lower delta S of vaporization there. Okay, again, just reasoning through this with ideas of how the orientation of the molecules in your substance plays into your entropy values. All right, hope that was helpful. Thanks.